I'm going to present to you a work produced by Vincent Gramoli, Seth Gilbert, and Pierre Civit, entitled Polygraph, a Countable Byzantine Agreement. The distributed computing community enjoys to tackle the famous consensus problem, where a set of n nodes want to eventually agree on a common valid value. Because of FLP impossibility problem, the approach is usually either randomization or partial synchrony assumption. Today we focus on partial synchronous paradigm. In this setting, the processes can be equipped with timer. They attempt to solve the agreement, and if they fail to decide before the timer expiration, they increase their timer and attempt again. Because of partial synchrony assumption, the timer will be eventually high enough to receive the messages from other correct, enough if they don't know the bound on delay for message transmission. Processes are also equipped with a public key infrastructure, so that they can sign their messages to ensure authentication, integrity, and non-repudiability. Such a consensus algorithm is not able to tolerate a number T of malicious nodes greater than n/3. This is even the case for a degraded version, where safety and liveness have to be ensured for k with 10 lower than n/3, and safety has to be preserved when t is greater than n/3. This is due to a famous splitting argument where a malicious majority of more than 1/3 of the consortium compute separately two contradictory executions with the correct nodes, splitting into two groups of less than 1/3 of the consortium. Because they can't distinguish this scenario with the correct one, they have to decide and eventually disagree when Q, the set of malicious nodes, is greater than n/3. This is a motivation to interest on accountable Byzantine agreement, that is, an algorithm that still solves the problem when T is lower than n/3, and that produces proof of culpability against n/3 malicious players when T is greater than n/3 and a disagreement occurs. During execution, the processes keep in their log the signed messages they received. We define some set of signed messages, which is called info alpha j, who are the signed messages collected at execution alpha by j, and alpha jk, who are the messages signed by k collected at execution alpha by j. A proof of culpability against j is a set of messages so that there is no execution where j is correct and cite these messages. To build an attack without accountability, a typical strategy is to design some indistinguishable executions alpha and alpha prime. In these mirror executions, the pieces of information collected by the union of correct nodes for only one execution are the same. So, that is, it's impossible for the correct nodes, C, to build a proof of culpability against nodes in C prime. If it would be the case, that would mean that it would also be possible after alpha prime to prove a correct node guilty. Thus, all the nodes in C cup C prime are said untouchable. They have an alibi, and the correct nodes are not able to refute this alibi. To attack a Byzantine agreement protocol, you have to design mirror executions B and B prime with a high amount of untouchable nodes, and be sure that the correct nodes can't expect additional messages before deciding and disagreeing. After network stabilization, the correct nodes I and J exchange their log but can't distinguish B from B prime. That's what we have done with PBFT. In PBFT, nodes progress through successive views. At each view, a primary receives some command M from client, attach a sequence number Sn to each command M, and start a classic three-phases protocol to commit the command. It pre-prepare, prepare, and commit. If a node receives two n/3 pre-prepare messages, it prepares M and broadcasts commit M. If a node receives two n/3 commit messages, it commits M and broadcasts commit M at sequence number Sn. When a timer expires, the primary is considered as too slow, and the backup broadcasts a view change message, propagating all the commands they prepared previously. And when the next primary receives two n/3 view change messages, it builds a new view message, which pre-prepares the commands that have been propagated. If no command has been propagating for sequence number Sn, the primary pre-prepares a special command, mnull, which means nothing has to be executed at sequence number Sn. We design an attack against PBFT in 3 views: V0, V1, and V2. In both scenario B and B prime, I receive 2 and over 3 commit messages to commit command M, while process J receives 2 and over 3 commit messages to commit M null at view V2. Then the primary of view V1 receives 2 n over 3 view change messages omitting M. Then it pre-prepares M null and sends new view messages to 2 n over 3 nodes that do not include I and J. Those nodes prepare M null and propagates this preparation at view V2. The primary of view V2 convinces everybody, including J, to commit M null. I and J disagree. After network synchronization, they realize that M null can have been pre-prepared only because more than n over 3 malicious nodes send commit M messages at view V0 without having propagating this command at view V1. But the primary of view V1 stay mute forever, hiding who lied. All the nodes who prepared M null at view V1 stay mute forever too. I and J will not be able to prove n over 3 guilty processes. In fact, they need a crucial piece of information: the set of view change messages received by primary of view V1. An intuitive solution would be to ask to propagate this set of view change messages. But we can use the same strategy, building a chain of malicious primaries who hide the set of view change messages who omit their preparation of command M at view V0. This observation led us to extend a leaderless algorithm, DBFT. This algorithm is based on a binary reduction, so we uniquely interest on a binary Byzantine agreement where nodes have to decide 0 or 1. Here again, the nodes progress through a succession of rounds. They start with an estimate value, exchange it, and produce a set val. Then, according to the parity of the rounds, they recompute their estimate value and decide or not. The set val can be either a singleton or the set 0 and 1. The estimation follows from the singleton or the parity of the round if val is not a singleton. This algorithm has a very nice property. If a correct node decides at round R, then all other correct nodes will have decided at round R plus 2. Thus, to cause disagreement, a malicious coalition has to tackle this property. To do so, they have to put the opposite value at round R plus 2. Let's fix Alice decided 1 at round 1, then Bob will accept 0 in set value at round 3. Bob is asking himself where is this value from. This is the estimate value of Charlie for round 3. This estimation has been motivated by the fact that this is the estimation of Dave of round 2. And this comes from a set of 2 n over 3 nodes represented by Eva, who sent the equivalent of a commit message for the proposal 0. But Alice also received 2 n over 3 commit messages at round 1, but for the value 1. That means that at least n over 3 nodes lied, but without the cooperation of Dave, Alice and Bob can't conclude. Thus, we ask Dave to justify its proposal with a ledger, encoding the messages received by the group of Eva. Then, we ask Charlie to propagate this ledger to justify its proposal. Now, in case of disagreement, Bob and Alice are able to produce a proof of culpability against at least n over 3 malicious nodes among the group of Eva. This is the principle of Polygraph, which solves accountable Byzantine agreement with a decent bit complexity. Thank you very much.